does the resistance of a wire depend on its length? Well, if you're from the education sector, which you probably are if you are here, you will know that this is a really important practical to the point that it's a required practical here in the UK, and there's every possibility that you are sick to death of it by now. Well, if that's the case, don't worry, I'm going to show you a way that you can zhuzh this practical up using the resistance wire board. And this is going to let you not only do the required practical, but also extend that investigation so that you can push your students that little bit further. And it will also provide a greater understanding of current carrying wires and their resistive properties. Now, you might be used to seeing a piece of wire sellotaped to a meter ruler for this activity, and you'll be able to see the similarities between that and the resistance wire board, apart from some key differences. Here you can see we've got 4 wires, not just the one, and each are of different thicknesses. Now this means that we can extend the practical to not just look at length, but also diameter. Further, the wires are nice and straight, so this is going to reduce the error in our length measurement. So the 4 investigations we're going to run through are: how does resistance of a wire depend on its length? How does it depend on its diameter? How does current depend on the wire diameter? And lastly, resistivity. So you can see that this piece of equipment is going to go way beyond the bare minimum, so let's get stuck in. Now the circuit that we need to set up is here, and if you see this and want to scream, don't worry, I'm going to walk you through step by step how to set it up. If you don't need this help, just skip me on to the next bit. So let's start with the most important one, the required practical of resistance against length of the wire. Now in the guide it says that you can use batteries for this, but I'm going to be using our mini DC PSU, which is called the battery eliminator, and his name reveals his identity. Now the whole purpose of this guy is to give you battery output voltages without actually using any batteries. It's perfect for circuitry work because you've got the 4mm sockets on the front, so you can easily patch them in. And it also means that you don't have to worry about batteries going flat or keeping a good supply of lots of different types of batteries. This guy can just waltz in and you can tune it to whatever you need it for. So equipment that you'll need: a battery eliminator, a voltmeter, an ammeter, a resistance wire board, a jockey, and some test leads. Okay, so getting everything set up, we want to go from the positive terminal on the power supply to the positive terminal on the ammeter. We then go from the negative terminal on the ammeter into the resistance wire board. Now the other side of the resistance wire board is the jockey, so I'm going to put a lead up that and then connect the other side to the negative terminal on the PSU. We then want to patch the voltmeter in parallel to the resistance wire board, so we put another wire in the jockey and put that in the negative terminal on the voltmeter. And then we go from the resistance wire board socket here into the positive terminal. The last thing to remember is to make sure that you've provided power to your battery eliminator, which just goes in the back of the unit, and it takes anything from 15 to 24 volts. So our circuit's set up and we are ready to start taking data. Our results table is going to have columns for the length of the wire, the voltage and the current, and we are going to take readings at 5cm intervals along the whole of the wire board. So to get our first data point, we want to make sure the battery eliminator is turned to on, and make sure the output is set at 1.5 volts. I'm going to turn the voltmeter on and the ammeter on. Then to connect the circuit all together, I am going to get the jockey and put it on the 5cm mark on the thinnest wire. Now to complete the circuit in this example, I am using the jockey, and that is because it's got a really well-defined contact point at the tip. So it just means that I'm going to get that length of wire bob on using this piece of equipment. So that's why I'm using that. So for the first data point at 5cm, I need to take down readings of voltage off the voltmeter and current off the ammeter, and then repeat the whole process at 5cm intervals. So the next one will be at 10cm, next one at 15, and so on and so forth until we get to 50cm. We can then use Excel to analyse the results and see what the graph looks like. So let's go there.
So here is the data for the resistance of the wire for different lengths. So to calculate resistance, all I've done is divide the voltage by the current, and I have plotted resistance on the y-axis against length on the x. And you can see this has given me this lovely straight line, and the linear fit function comes out as this. So you'll see there's no y-axis intercept, like there's no plus or minus a constant here. So this shows that my data goes through the origin, meaning that at zero length, there's zero resistance as expected. Now the gradient that's fitted here, let's head over to the whiteboard to see what it's equal to.
To run through the maths, the equation for resistance is equal to resistivity times by the length of the wire, all divided by the cross-sectional area. So if we plot resistance on the y-axis against length on the x, we are left with resistivity over cross-sectional area, and that is going to be our gradient.
So getting that proportional relationship from the graph is the whole point of the experiment, but we can use this gradient if we wanted to, and we can use it to work out d, the diameter of the wire, and we can check that it's right using vernier calipers. So for this, we want to use the resistivity value from the instruction manual, which I've typed in here. Then we can work out the area by using the resistivity over the gradient, which I've done here. And then we can work out the diameter by subbing in pi r squared into the area equation and then subbing in for little d as well. And then that gives us a measured value of the diameter of, what is it? 0.384 of a millimeter. And then if we compare that to the actual value of D, which is zero point 0.4 millimeters, we see that we come to within 5% error, which is really good. So this gives you the option to go one step further with the maths, and then it gives you an excuse to whip out the calipers and to take some readings from a vernier scale.
Now, from our results, we can see that as we increase the length of a wire, its resistance is also going to increase. And that relationship is proportional because we get that nice straight line graph. Now, this is important because it means that the longer the wire, the more voltage drop we're going to get, and the more heat loss is going to occur from that increase in resistance. So this is when it becomes clear that if we want to send a voltage a long distance, we need to put some serious thought into the mechanics of how we're going to do that. And that's a really nice question that you can ask your students to see if they're starting to grasp the principles that we're trying to teach here. Now remember, we've got 4 wires to play with here, not just the one, so we can repeat that process for all the wires and see how the diameter is going to affect the gradient of that graph. I'm going to do that and share that with you.
Okay, so this is a busy spreadsheet, but here is my resistance data for all 4 wires. Now, if I plot this all on the same axis, you will see that the diameter is having an effect on the gradient of this graph, but this shouldn't be a surprise, right? The gradient is a function of resistivity, which is itself a function of diameter, so we would expect this to change. But how can we make use of it? Well, if we plot the gradient against 1 over a, this essentially means that we're multiplying out the area from the function. And so we are left with a gradient on this plot of resistivity. So just to walk you through that, when we measure the gradient, we essentially divide what's on the y-axis by what is on the x. So you might have seen this equation before, or you might be able to relate it back to the differential dy by dx. And doing the maths, if we divide rho over a by 1 over a, it's the same as saying rho over a times by a over 1, which leaves us with a gradient of rho, which is the resistivity on its own. So this means we directly take the gradient from this graph and compare it to the known resistivity, which is in the book. And when we do the percentage error, we get like 7.5%, so easily within 10%. And this gives you a nice way to have a quick look at resistivity and get creative with your graphing techniques.
Now, you might find it difficult to get a good data set for the thickest wire in this case, and it's just because it's carrying a lot of current at this point. But don't worry, you can still get a really good result from the first 3 skinny wires, so let me show you in Excel what I mean. Now our results are showing that the diameter or the cross-sectional area of the wire is having an effect on the resistance, but we can do that investigation more robustly, and for that I need a continuously variable power supply, so something a bit like this. So I'm going to swap out the battery eliminator for this, and this is because I want to make sure that the voltage that I'm applying across the wire is going to be consistent for each diameter. So let's do that. Okay, so for this investigation, looking how diameter affects the resistance of a wire, in the table you're going to want to have columns for the diameter of the wire, which you can either get out of the instruction manual or you can measure it using some vernier calipers. You also want a column for voltage and one for current. So let me show you what to do. We are going to get our jockey and put it on the 25 centimetre mark on the thickest wire. And when it's on there, we want to adjust the power supply so it reads 1 volt on the voltmeter. So I'm slowly going to increase this until we get to about 1 volt. And then I'm going to take the current reading off the ammeter. I'm then going to put it on the 25 centimetre mark on the third wire and adjust my power supply until my voltage goes back to 1 volt. There we go. And again, take the current reading. I'm then going to put it on the second wire, adjust the voltage for 1 volt, take the current reading, and do that for all 4 wires. And then we can go back to Excel, plot the results, and see what we get.
Okay, so here in this first plot, I'm plotting resistance on the y-axis against diameter on the x. And this produces a power plot, which when we fit gives us an order of minus 1.859 as the fitted power. So this rounded to the nearest integer is 2. And if we check with the equations, you can see that this is exactly what we expect. Resistance should go as d to the minus 2. Now, all I've done here is just sub in for pi r squared in this equation, and it gives us the relationship between resistance and diameter. And while we're here, we can also plot current on the y-axis against diameter on the x. And again, we get this power relationship. And when we fit this in Excel, it refines the order of the equation to positive 1.8595, which again, we can round to the nearest integer, which is 2. And comparing this with the maths, this is exactly what we expect. So here, all I've done is sub in R equals V over I and got this relationship, and then made I the subject so we can see how it varies with diameter. So here you can see that we expect current to go as diameter squared, and this is exactly what our data proves. Now, these are 2 really important results as they show that as diameter increases, the resistance drops and the wire can carry more current.
So we have covered how you can extend this practical using this piece of equipment. So we've drawn some really nice conclusions, like the resistance of a wire increases with its length, but decreases with its diameter, and both at different proportions. And we've also learned a really nice way that we can work out resistivity of the wire. Now, this leads into some really nice conversations that you can have with your students about power losses and efficiencies and how the national grid works and how you transfer a voltage across very large distances. So I hope this has been useful. Please let us know in the comments if there's anything else you'd like to see. And here's to the next generation of electricians and electrical engineers. Thanks very much for watching.